Hi, and welcome to the last section of the waves theme. And we're looking at the Doppler effect today. Doppler effect, again, another really interesting topic. I actually really love waves. It's not very long. There's a couple of shortish concepts that you need to understand, a couple of formulae that look difficult but are not really, and I'll show you a trick on how to make sure you get them properly. But otherwise, a great topic. So it's as usual, okay? You've got your learning objectives checklist. You've got your revision note template, you've got your knowledge question and answers. You should know how to use them by now. If not, it will be very clear within this tutorial. That's me doing an impression of a Formula 1 race. What do you think? Well, the reason cars sound like that, well, not exactly like that, but the reason cars sound like that is because of something called the Doppler effect. The Doppler effect basically changes the waves that you observe when you're looking at something moving. And I'd like to look at that in more detail now. So I really only want to, at this stage, think about sound waves. And let's consider a fire engine. And let's consider a fire engine that is stationary. So if you think about a fire engine that's still and stationary, it emits sound waves in all directions. And you can see I've represented that here with these rings around it. These are sound waves. Okay, you can see that they're equal distance apart. That means the wavelength is constant. And they'll be travelling at the speed of sound in air, which is 340 meters per second. That's fine, isn't it? Okay, they travel equally in all directions. And if you were to stand on this side, or this side, and listen to these sound waves that have been emitted by the fire engine, they've all got the same wavelength, they've all got the same frequency, they've all got the same sound. So this guy here and this guy here will hear the same sound, which is when they're stationary. You know what's coming next, don't you? Let's go to the next page. What happens when the fire engine moves? Well, if it moves towards the waves it's just made, it kind of catches up with those waves. And you can see that the wavelength, because it catches up and they bunch up together, the wavelength gets smaller in the direction the fire engine is moving, and the wavelength gets bigger in the direction behind it. If the speed's the same, because speed has to stay the same, nothing's going to change about the speed of sound in air, that means that the frequency must get bigger, and on this side the frequency must get smaller. There's less waves passing a point per second. A larger frequency, so let's go to this side. A larger frequency, a bigger frequency, is a higher pitch, so E. And a smaller frequency on this side is a lower pitch. Let me do my noise again from a Formula 1 race. It gets a higher pitch as it's coming towards you, and as it goes away from you, it goes down again. And that is basically the Doppler effect. There's an apparent change in the frequency of the waves. This is only to the observer. So if we look at these guys again, number 1 and number 2, these guys are observers, and they observe that the waves have been bunched together here to have a higher frequency and spread apart here to have a lower frequency. There is a ratio factor here. If this frequency increases by 2, then this frequency goes down by a half. If this frequency increases by a factor of 3, then this frequency decreases by a factor of a third. So there's something to bear in mind there. But it's not only sound. We can do it with light too, because light is a wave, right? If we think about a lower frequency, a longer wavelength, we're looking at red light. And if we're looking at light with the observer, the source moving towards it, we're looking at a higher frequency, a lower wavelength, we're looking at blue light. So actually, if something emits light and it's moving away from you, then you would experience it to be more red. And if it's moving towards you, you'd experience it to be more blue. Obviously, this has to happen at relativistic speeds. But with sound, it doesn't have to be relativistic speeds because the speed of the sound wave is much, much smaller. Now, this is really, really important. These waves, yes, their frequency changes, yes, their wavelength changes, but the speed of the wave, v, is always the same. It doesn't change. As long as the material stays the same. I mean, if it goes into water from air, then the speed of the wave is going to change. But as long as the medium of that wave is the same, then the speed of the wave itself is always the same. It's only how the waves relate to each other, either they bunch up or spread out, that changes that wavelength and frequency. If you were asked to explain the Doppler effect or describe the Doppler effect, the sentence you would use is the Doppler effect is the shift in frequency due to the relative motion between source and observer. That's as precise as we can get it. I would probably go to common diagrams section here, and I'd try, if you can, to draw this diagram here, or both of these diagrams. It's not easy. Little note, you might be expected to draw that. Ooh. So a little practice of that might be a good idea just now. You don't have to draw a fire engine, but you can draw something that makes a sound. And then try and draw these waves bunching up and going behind you. Make sure you know that the object's moving that direction. I would say wavelength decreases, frequency increases. Wavelength increases, frequency decreases. So let's have a look at a couple of situations where the Doppler effect is useful. You can see a picture here of a policeman, and he is measuring the speed of cars coming towards him. So he's a speed cop, right? And what he's actually using is the Doppler effect. His radar gun, it bounces a microwave signal off of the desired target. So it would be a car in this case. And by analysing how the object's motion has altered the frequency of the return signal, you can actually get a very direct and a highly accurate measurement of the target's relative velocity. Now, the term relative velocity is important. That means that the policeman has to stand still. He's the observer, and he has to stand still. And at this point, the source is moving towards. Now, we'll think about that when we look at the formulas later. But basically, yeah, you would measure the speed of a car using the Doppler effect by bouncing microwave signals off the moving car towards it and analysing the wavelength of that microwave signal as it returns back to the gun. Another situation is ultrasound. So you would, if you're unlucky enough to be in hospital and you need to analyse the flow of your blood or to look for blockages in your blood systems, then you would use an ultrasound. Well, you wouldn't use it. The doctor would use it. So in an ultrasound scanner, there's a series of pulses that are transmitted to detect the movement of blood. So there's ultrasound pulses transmitted into your body. Echoes from stationary tissue come back with the same wavelength because that's not moving, right? So you've got your ultrasound, it releases a wavelength of, lambda, and it comes back the same wavelength because nothing's moving. However, the reflections or the echoes from moving blood cells exhibit slight differences in the time for the signal to be returned to the receiver. So if the blood cells are moving away from us, then the time would be longer. And if the blood cells are moving towards us, then that reflected echo would be shorter. And using the Doppler effect equation or the formula, you can work out the speed of these moving blood cells. And obviously really clever doctors know how fast blood should be moving in your veins. And they can say, oh, right, there's a blockage here, or this is not moving as fast. And then that's how they work out the speed of your blood and do very clever things to make you well again. You'll notice we've given two examples. One was the police speed camera, and that used microwaves. They are electromagnetic waves. And the other was the ultrasound, and that used sound waves. There are two very clear types of waves. There's electromagnetic waves and sound waves when we're dealing with the Doppler shift. And we're going to focus now on electromagnetic waves. And more specifically, we're going to look at how the electromagnetic radiation emitted from distant galaxies and stars can help us make assumptions about the universe. Okay, we've got a picture here, and bear with me on it. If you take some glowing hydrogen gas in a tube and you analyse it with a spectrometer, what it does is it splits out the light of that gas, that glowing gas, into different wavelengths, and you get a spectrum. And that spectrum has glowing lines at certain wavelengths. Now, given that new stars, very far away, that are just being born, are mainly made of hydrogen burning, then when you analyse the light from a very distant star, you should just be able to see hydrogen burning. You can split it out using a spectrometer, and you should see exactly the same spectrum. And what we can see is, when we analyse these spectra and they're examined, they're found to be shifted towards the red end of the spectrum. And this shift is apparently a Doppler shift, which indicates that all the galaxies are essentially moving away from us. And that's one of the main pieces of evidence for the Big Bang. Let's expand on this concept of the Doppler effect and galaxy redshift. In this slide we have two spectra. It's a spectra from the same element. And you can see the pattern looks largely the same. There's a strong line in the red spectrum, there's a strong line in the yellow spectrum, there's a double line as it approaches green. But one spectra is shifted further into the red end of the spectrum. And I keep saying it's shifted towards the red end of the spectrum. What do I mean by that? If we look at the left spectrum, the spectrum on the left is the absorption lines in the visible spectrum of the Sun. And for the purposes of the universe, the Sun is stationary to us. So we're saying this is a stationary spectra relative to us. We can analyse that spectrum and find the wavelength of each of the lines in the emission spectrum. If we analyse the absorption lines from a visible spectrum of a supercluster of distant galaxies, we believe they are moving away from us, and they're very distant. We know that it should be the same, but everything's shifted, and the shifted wavelengths all seem to be a little bit shifted towards the red end of the spectrum. They're a little bit longer. And why is that? Let's consider a distant star that's moving away from us. It emits light in all directions, but because it's moving away from the light that it's previously emitted, we get this pattern of waves again that we've seen before. The direction that it's moving away from means that the waves tend to move apart and the wavelength increases. An increased wavelength means it shifts towards the red end of the spectrum. The direction it's moving towards bunches up, the waves all bunch up, and the wavelength decreases. The frequency increases, and that end of the spectrum is blue. So if the galaxies were moving towards us, we'd see a blue shift, and all these spectra would have moved that way. But the fact that they have red shifted means the galaxy is moving away from us. So you may be saying to yourself, why the heck are we always talking about redshift? Well, imagine this is us on the Earth, and these are all distant galaxies. Every distant galaxy that we observe has a slight redshift in their spectrum, which means all those distant galaxies are moving away from us. That leads us to believe that the universe is expanding. Of course, there's the odd galaxy that's moving towards us and is blue shifted, but that's on a localized level. On a larger, more generalized level, everything is moving away. It's expanding. And this is the reason galaxy redshift of the spectra is the reason that we believe the universe is expanding. Sorry, it's one of the reasons we believe the universe is expanding. When we're looking at electromagnetic waves, we do have a Doppler effect equation that measures the amount of redshift or blue shift that an object has. And this redshift equation is pretty intuitive. Delta lambda is equal to the shift in wavelength. So if we take this diagram, for example, let's say that wavelength is 500 nanometers and this one is 510 nanometers, then the change in wavelength here would be 10 nanometers. Lambda is the wavelength when it's stationary, and in this case that would be 500 nanometers. V, speed object is moving. And in the previous example, that would have been how fast the galaxy is moving away from us. And c is the speed of light. You'll notice we've given the term z the redshift term, and that's just a number. That's a number depending on what these ratios are of wavelength and speed and so on. One of the interesting things to note, if I take this equation and rearrange it slightly, and let's consider, for example, a distant galaxy. Let's say a distant galaxy is moving away with speed v, and the speed of c is the speed of light. So this factor here is a constant if the galaxy is moving away at the same speed. That means as the wavelength of the spectra increases, this wavelength here, i.e. goes towards the red end of the spectrum, we should expect the change in wavelength to be bigger. You'll see that the shift in wavelength here is actually bigger than the shift in wavelength between these two. And that's because the wavelength of red is greater than the wavelength of green, meaning this delta lambda factor is going to be greater as it shifts through the red end of the spectrum. In the data booklet, your Doppler effect equation is actually given in this term. And the reason we can do that is because C equals F lambda, F equals C over lambda, and we can then substitute that in to give us the equation and give us this idea of frequency in that equation as well. It just makes it a bit easier to analyse, and this is the equation that's given in the data booklet. We talked earlier about how all the galaxies seem to be moving away from us. And one of the key elements that Hubble found was that nearby galaxies, yes, are redshifted, and you can see here an indication of the shift by these arrows. Galaxies a bit further away, they seem to be shifted a bit more. And really distant galaxies were shifted even more. What he found was the further away they are, the faster they seem to be moving. And that prompted him to come up with Hubble's law. He said the speed of recession of the galaxy is equal to Hubble's constant times the distance the galaxy is away. And the Hubble constant is a constant which tells us that the speed of recession of the galaxy is directly proportional to the distance it is away. And the gradient is equal to Hubble's constant. Now that's Hubble's law, and that tends to come into the idea of cosmology more than in this section here. We previously talked about the idea of a speed trap. Let's look into this in a little bit more detail. The police radar gun emits a microwave of frequency f0. If the car is moving towards it, that car is going to experience a higher frequency, and if the car is moving away from it, that car is going to experience a lessened frequency. And this frequency shift, using the equation we talked about in the last slide, gives us an idea of how fast the car is moving. C in this case is the speed of microwaves, which is an electromagnetic wave, so it's 3 times 10 to the 8 meters per second. And if we know the initial frequency of the wave, then we can find out what the speed of the car is. However, there is an effect you do need to be aware of when we're looking at police radar guns. It's called the double Doppler shift. I want you to consider this microwave gun. It's releasing a frequency f0, and as it's being released, a car is approaching it, which means this car is experiencing an increased frequency depending on how fast it's moving. But what happens is this car then reflects that increased frequency, so it reflects it as it's approaching, which means there's a double Doppler shift there. Because it's reflecting as it's approaching, this Doppler shift is applied twice. First, it's a moving observer, and second, it's a moving source. And because it's an electromagnetic wave, we are able to use this equation, but we've got to put in a factor of 2 here to reflect the fact that it's a double Doppler shift. So if you see this, or if you're looking at anything to do with police radars or reflection of police radars, then you've got to remember to put that factor of 2 in. So I've mentioned the Doppler effect formula once or twice. It's now time for us to look at it in detail. And this is where students tend to get, oh, it's so complicated. It's not, right? First of all, the formula is given in your data booklet, and it's actually labelled moving source, moving observer. So as long as you can look at a question and work out if it's the source, like the thing that's making the sound that's moving, or the observer that's moving, then you know which equation to use. But the tricky thing is, do you use the plus or the minus? So let's look at that in more detail. Let's first of all look at the moving source. So let's imagine we've got a source that emits sound waves, and we've got the observer here. In this situation, the source is moving towards the observer. We're going to find this situation here. Oh, excuse my drawing. We're going to find it's all bunching up towards the observer. Okay? And in this formula, f dash is the observed frequency, or the apparent frequency. F is the original frequency. So it'd be f dash here, f here. V is the speed of the wave, and us is the speed of the observer. Just using common sense, we would expect that this observer here is going to experience a frequency that's higher than the original frequency. So we expect f dash to be greater than f. So this is going to be bigger than that, which means that this factor here has to be greater than 1. And for that factor there to be greater than 1, this needs to be a negative, because that number will be small, and that one, this number will be smaller than that one, which means it's greater than 1. So if you have a moving source towards the observer, then you use f dash equals f v over v minus us, because you expect the observed frequency to be greater. No surprises then if you have a moving source away from the observer. Let's draw that. So we've got a moving source, it's moving away from the observer. There's the observer here. The observer experiences f dash, this is f, this is moving. We expect this frequency here, f dash, to be less than the original frequency. If it's less, then this factor here, it should be less than 1 to make that number smaller. So if it's got to be less than 1, then this has to be a plus. So the formula you'd use if there's a moving source away from the observer is v over v plus us. And remember, us is the speed of the source and v is the speed of the wave. So this time we have a source, it's giving out waves, but it's not moving. So the wavelength is going to be steady. Just imagine they're concentric circles, okay? And it's giving out a frequency f. And we have an observer that's moving towards it with a speed of u-o. That's the speed of the observer. And we want to know what frequency they're going to experience. Well, as they move towards that, then they're going to experience these waves faster than they were emitted. So they're going to experience a frequency dash, which is greater than the frequency that was emitted. And if the frequency's got to be greater, then this factor has to be greater than 1. And for the factor to be greater than 1, we have to use the plus. So if you have a moving observer towards the source, then your equation is f dash equals f v plus the speed of the observer over the speed of the wave. And you guessed it, the last one here, if we have a moving observer away from the source, then this factor here has to be less than 1 because the f dash has got to be less than the original. So that means this has to be the negative, so f dashed equals f v minus u naught over v, and that's your equation for that. It's really up to you now to practice that equation, and I'm going to put lots of questions in this tutorial for you. You can go and tick off those learning objectives now, but before you tick them off with massive confidence, let's do a couple of things first. Write down the definition of the Doppler effect in your notes, as we discussed. Give 3 explanations of the 3 situations we'd use it. The 3 ones I'm interested in and the IB are interested in is the ultrasound, the radar for measuring speed of objects, and the redshift. And then the third thing to do is try the questions in this tutorial, and of course you'll get the answers too. Thanks very much. See you later. Bye.